It all kicks off with a really simple question. We have a single charge sitting in space. How does it change the very fabric of that space around it? We know it creates an electric field, but how do we describe the energy landscape it sets up? How could we measure the electrical height in any given spot? Well, that's exactly what we're about to figure out.
So here's our game plan. We'll start with the principles we already know. Then we'll dive right into the derivation, taking it one logical step at a time. After we reveal the final formula, we'll spend some time unpacking what it actually means and, maybe most importantly, why this whole thing matters so much.
All right, any good expedition needs a solid base camp. And for us, that means getting our tools in order. We're going to need two key concepts to start this climb.
Okay, our main tool is the formal definition of potential difference. It tells us that the change in potential, VB minus VA, is equal to the negative integral of the electric field, E, dotted with our path, dr. Now, I know that integral can look a little intimidating, but trust me, it's the engine that's going to power this entire derivation.
And our second tool is something you're probably pretty familiar with, the formula for the electric field coming from a single point charge Q. The field E is just Coulomb's constant K times the charge Q, all divided by the distance squared, r squared. This is the key piece of info we're going to plug into our main tool.
Okay, we've got our gear. It's time to start the climb. We are going to solve that integral, but don't worry, we're going to take it one easy, manageable step at a time.
So our very first move is simple substitution. We just take the general E from our definition and swap it out with the specific formula for our point charge. So our integral becomes the negative integral from our starting point RA to our endpoint RB of K times Q divided by R squared. Next up, let's clean this up a bit to make our lives easier. You see, Coulomb's constant K and the charge Q, they don't change as we move along our path, right? They're constants, so we can just pull them right outside the integral. Look at that. It already looks so much simpler. Now, before we actually do the calculus, here's a classic little trick. Instead of writing 1 over r squared, we're going to use a negative exponent and write it as r to the power of negative 2. It means the exact same thing. It's just written in a way that makes it super easy to use the power rule for integration.
And here it is, the heart of the math. We're going to apply the power rule. We take our r to the power of negative 2. The rule says you add 1 to the exponent, so negative 2 becomes negative 1. Then you divide by that new exponent. So we have r to the negative 1 divided by negative 1, which just simplifies to negative 1 over r. And just like that, the hard part, the calculus, is done.
Hey, notice what just happened there? We had that negative sign sitting outside the integral from the very beginning, and the result of our integration also gave us a negative sign. Well, those two negatives cancel each other out, leaving us with this much friendlier positive expression, KQ times 1 over r. We still have to evaluate it, but it looks a lot nicer.
We're in the home stretch now. With the calculus done, all that's left is to plug in our endpoints. We take the value at our upper limit, RB, and then we subtract the value at our lower limit, RA. This gives us our final answer for the potential difference. It's K times Q, all multiplied by the quantity 1 over RB minus 1 over RA.
And there we have it. We did it. We successfully navigated the integral, and we have reached the peak of our derivation. Now it's time to just sit back, admire the view, and see the simple, beautiful truth that was waiting for us all along. So let's look at what we found. If we just distribute that KQ term inside the parentheses, something really remarkable pops out. The potential difference, VB minus VA, is just a term that looks like KQ over R for point B minus the exact same structure for point A. Now that's not a coincidence, it's a huge clue. Because what this pattern is telling us is, well, if the difference between 2 points always looks like this, it must mean we can define the absolute potential, V, at any single point in space with this stunningly simple formula. The electric potential is just K times Q divided by R. All of that calculus, all of that work, boils down to this one elegant little equation. So we have our formula. But, a formula is only as powerful as our understanding of it. What is this equation actually telling us about how the universe works? The potential, which we call V, at any given point in space really just depends on two things: the charge itself, Q, and how far away you are from it, R. You can think of this formula as a map, charting the electrical landscape that this one charge sets up. And the relationship here is super intuitive. The farther you get from the charge, the weaker its influence becomes, so the potential naturally drops off. It just makes sense, right? Distance softens the effect.
Okay, so talking about an electrical landscape is one thing, but what does it actually look like? Visualizing it is what really makes it all click. And you'll see for positive and negative charges, the picture is completely different.
And this is where a really great analogy comes into play. Picture a positive charge creating a hill of potential. It's really high right next to the charge, and then it just slopes down in all directions as you move away. A negative charge does the opposite. It creates a well. The potential is a big negative number right at the center, and it kind of climbs back up towards zero the farther out you go. This hill and well model, it's going to be incredibly helpful.
So, we have our landscape, we've got our hill, or we've got our well. Now comes the most important part. We're going to bring in a second charge and see what happens. This is the moment potential finally transforms into energy. And there it is. Potential energy, U, is born from this interaction. You just take the value of your second charge, Q2, and multiply it by the potential, V1, that the first charge already created at that exact spot.
Exactly. You rearrange it slightly, and the standard form is U equals KQ1 Q2 divided by R.
So here's the key takeaway. Energy isn't a property of one charge sitting alone. It's a property of the system. It absolutely requires an interaction.
Awesome. So we know how to handle the energy of a pair of charges. But what about when things get more crowded? What if we have a system with 3, 4, or 100 charges?
You might think it's going to get really complicated, but the principle is actually surprisingly simple. To find the total energy of the whole system, you just have to be methodical and add up the energy for every single possible pair. The key is to count every unique interaction, but not to double count anything.
So let's imagine we have 3 charges. We just need to be systematic. First, we find the energy between charge 1 and charge 2. We'll call that U12. That's our first pair.
Next, we calculate the interaction between charge 1 and charge 3. That gives us our second piece of the puzzle, U13. And of course, we can't forget the last possible unique pairing, the energy between charge 2 and charge 3. That's U23. And just like that, we've accounted for every connection in the system. So to get the grand total, the total energy of the entire system, you just add them all up. It's a simple sum, U12 plus U13 plus U23. It's completely additive. And if we had a fourth charge, we just find all the new pairs it makes with 1, 2, and 3 and add those energies into the pot as well.
Okay, we've gone on quite a journey here, from the potential of a single charge all the way to the total energy of a complex system. So let's boil it all down to the most important takeaways.
Here's what you've got to lock in. First, potential, V, is a property of space created by just one charge. It sets the stage. But potential energy, U, that's different. That's a property of the interaction between 2 or more charges. Remember that this energy is literally the work stored to build the system. And finally, to find the total energy for any system, you just sum up the energies of every unique pair.
And I'll leave you with a final question to think about. If you go through all the math and you find that the total potential energy of a system is a negative number, what does that actually tell you about the system? What does it imply about the forces holding it all together? Something to chew on. Thanks for watching.